Second debate tonight, and the topic this time will be reversible computing and also examining or discussing the validity of the Landauer principle. And to get started, we'll break this down into 4 questions, and we have a pro team and a con team, but some people will kind of switch back and forth between the pro and con sides. So just to get started, we've laid it out so far as on the pro team we have Neal and Renato here to my right and to your left. And then for the con team, but again, maybe switching back and forth, we have Ferdinand here, Robert, Wolfgang, and Laszlo. And so for the questions that we'll look at, the first one will be reversible computers, are they possible? And if so, do they violate thermodynamics? And also we'll talk about Brownian computers, if they're possible, and if so, do they dissipate more heat than conventional computers? The third topic or question we'll look at is which dissipates more heat, erasing information or writing information? And then the fourth topic will be Landauer's principle, whether or not the panelists think that it's valid, and also can it be applied to writing information, or is it only for erasing information, or is Landauer's principle just simply invalid? So why don't we go ahead and start and tackle the first issue of reversible computers, and start with the pro team. Ms. Neal.
As far as the possibility of reversible computing goes, I think it depends on how you define reversible computing. And my answer would depend on the version of the question, or the definition. If reversible computing means that you don't pay a price for losing information, and you're not losing information in the reversible computer, then I would say yes, it's possible. If the question is rephrased as is there a fundamental limit that's greater than 0, it depends on what you call fundamental. There may not be a Landauer cost, meaning a cost of information erasure, but there may be other things like thermal fluctuations that may in some way affect the bound. So if reversible means 0, and we're saying is it possible to make a machine that computes and dissipates 0, and we're talking about actually realizing it, then the answer is, it's probably easy to answer that question no with a fairly high level of confidence. But I don't think that's the real question. I think it's could you get down below down below what the Landauer limit would be for an equivalent machine that does the same computation irreversibly, and you have to pay the Landauer cost. So this is a significant question these days, because electronics has scaled to the speeds and densities such that we're not that far away from heat dissipation limits, practical heat dissipation limits, even at the Landauer cost. So it may be possible that you don't have to go to 0, but you can possibly make computers that use reversible logic and do better than we would otherwise be able to do by more conventional approaches. So there are a variety of ways to think about the question, and my own personal answer to the question would depend on how you phrase the question and define the terms.
So apparently there's no common definition of what reversible computing even means, but for me it means that it's a machine or a computing machine where the information degree of freedom don't couple with the environment. And by environment I mean all other degrees of freedom of the machine that are not dedicated to carry information. And if this is of course the case, then logical reversibility corresponds to actual physical reversibility. So that's the definition I take here, and I would certainly also agree with Neal that we will never achieve that perfectly. So even with that definition, although this definition is slightly differently, so we will never have a machine where these information dealing degrees of freedom don't couple at all. But the question is, how close do we come to this ideal? So one remark that I would like to make is that if you want to build a quantum computer, which will of course be a question of tomorrow's debate, then this is strictly, or this is at least as difficult as building a reversible computer. That's what we know. So in some way, once we can build a quantum computer, we also know that we can build a reversible computer. And the reason is very simple. The quantum computer, as soon as the information degrees of freedom couple with anything else, then we have decoherence. And so either we now can correct, or either it's so small that we can correct for it, or it simply doesn't work. So if we are, or if someone is convinced that we can build a quantum computer, which is probably not the case for this team, one could also build a reversible one. But just to make this connection explicit. Now, of course, no reversible computer has been built, and experiments will show. But I'm not aware of any fundamental living or physical reason that will prohibit building a reversible computer. There may be such limits, but I haven't also seen a convincing theorem that gives the power. And if someone says it's not possible, then because, as we just both said, we will never achieve it perfectly, I would expect that such a statement should declare bound and say it's not possible, and this is the bound. And if you just say we cannot perfectly achieve it, then I don't think it's an interesting statement. So a statement should have a strictly non-zero bound on the coupling between the information degrees of freedom and the physical ones. And I don't see where such a bound should come from. And so therefore, I'm actually quite convinced that it's just a matter of technological progress until we can come close to a perfectly reversible computer.
You think that will happen in your lifetime, our lifetime?
If I see the progress that is made by those people who try to build quantum computers, then I'm pretty sure it will be, assuming that I live for another 20 or 30 years.
Okay. All right, and so in the Khan team, how about you, Ferdinand?
Okay, so I think logically reversible computers, of course, are absolutely possible, but of course I don't expect zero energy consumption from them. And the reason is, well, first of all, fluctuations, and I will not comment on that because I think the other team members will comment on that. I will focus on another reason, and that is one implicit assumption that doesn't seem to be voiced very often. That is that in reversible computing schemes, they are all clocked. So, and maybe we should go back. Why is there clocking in computing? In computers. Okay. Why is there clocking in computers? It guarantees that all logic gates have time to settle down in a stable state before their outputs are validated. And all those reversible system proposals only look at the times corresponding at the clock, when the clock comes in. But they don't look at what comes in between. So basically you have signals that wait at the gate for a clock pulse to arrive, and then you do your operation and you get the output from your logic gate for the next stage. But waiting is basically an irreversible operation. So if you stop, if you have something stopped and it is reversible, then it will never start. So to eliminate waiting, maybe we should tune the length of all our wires between the gates to exactly the right length. And if that is even possible. And then another point is concerning clocking. A clock basically pumps energy into your system at regular intervals. So what is the point of looking for a zero energy computation if you need energy for the clocking in the first place? So that's my answer.
Okay, maybe I will use the label because I would like to refer to the definition of Renato. I mean by reversible machine something which works according to some Hamiltonian dynamics, both classical and quantum. We cannot avoid today also quantum computing. And this is situation very clear in classical physics, and there is a lot of evidence also in quantum what is going on. If you think about this set as a phase space of the classical system, and this is classical system which can be used as a computation device must be essentially complex. So it means that it's also a chaotic system. And if we start with some point and add arbitrary small noise, then one can show that the probability distribution becomes spread out, and the volume of this part of this phase space where the probability is substantial of this probability distribution grows exponentially with time. So essentially this is this coefficient is the sum of Lyapunov, positive Lyapunov exponent or Kolmogorov-Sinai entropy. So this means that a probability of getting a right answer from the computation is exponentially low with time. Therefore, you cannot build a scalable computer using a classical chaotic system. And the main plot is the following. The entropy of the distribution grows linearly in time, and the slope is something what is called dynamical system theory Kolmogorov-Sinai entropy, or the sum of positive Lyapunov exponent. And exactly the same picture is in quantum situation. If you add arbitrary small noise to the quantum system, which is complicated, it means chaotic, the entropy, there is a notion of dynamical entropy here, and the same picture appears. So it means that the probability of finding a given answer becomes exponentially small. And this is, of course, not a mathematical theorem, but there is a lot of numerical evidence for many examples, which in my opinion, from the very beginning, killed the very idea of quantum computation. But nobody thinks in these terms about this problem. So there is for me no difference between Hamiltonian analogous classical computer and quantum computer.
So I would like to give a more practical answer, and I think one needs to go back to, in talking about reversible computation, what is computation? So computation fundamentally is and this is quite amazing actually, that any computational problem can be reduced to a few elementary operations and sequences of these elementary operations, which allows you to implement in hardware a computational system by realizing these simple operations. But then you have to make sure that your computational path follows the logical path. And everything has to operate, of course, in the presence of thermal noise, and so one has to ensure that your computation stays on track, that you're not being thrown off by random thermal noise. For example, what I talked about before in my talk, a fundamental process of computation, of this model of computation is you have to read the state of the operation. This reading has to be done in the presence of thermal noise. And if you just read thermal noise, then of course your computing is just going to be a random walk in the computational space, and it's not computation anymore. So just to make an analogy, so computing in this sense corresponds to, let's say, a boat, a ship in the ocean, and it's supposed to stay on a particular track, which is pre-described, which represents your computational path. And in order to stay on track, this boat, of course, has to battle noise, which are the waves, right? And so you need some energy to do that. If you don't pump energy into the computational process, then your boat is just going to be thrown around by random thermal noise, and you're not going to stay on track anymore. And exactly the same applies for computation. So I think reversible computation is impossible in the presence of thermal noise. Renato talked about reversible computation being the computational variable completely isolated by thermal noise. But this is not the model of computation that I think one talks about when talking about a Turing machine. This is an automaton. One can define certainly a piece of hardware which implements the whole computational path and trying to isolate it from the environment. But a system like that performs one task and one task only.
Yes. So are reversible computers possible? No. Or do they violate thermodynamics? Yes. I have similar opinions, so that basically the argument is also similar. Whenever you do a single bit operation, then you have to invest at least kt times logarithm, natural logarithm, 1 over epsilon energy, where epsilon is the error probability of the operation. This energy will be lost because it has been damped when you did the operation. Any effort to save this energy would result in more energy dissipation than just damp it. This is the reason why you have this energy due to the thermal noise, because you have to put the states into a potential well to avoid spontaneous switching between the states. Then what I want to say here is that, concerning Renato's point that it would be like a computer which would be not coupled basically to the thermal bath. Now this computer is coupled to thermal bath due to this friction that you have to damp the system after changing the state. And also I agree with Wolfgang that this would be actually, if you imagine a computer where this would not be coupled to the friction-free computer basically, that would be, he calls this automaton. I have a very simple example for that. You could have an RL resonance circuit, which would be, you kick it and it would do a sinusoidal oscillation. You could use this to generate a periodic bit sequence, periodic 0-1 bit sequence. This oscillator would run, if it is loss-free, for infinity. It would generate you for free periodic bit sequence. But it would not be able to generate information. The information in periodic bit sequence is information channel capacity of that is 0. To have information, non-zero information channel capacity, you would need arbitrariness in the whole system, and that needs the friction. Thank you.
Okay, so should we go back for round 2 on this, or do you want to just go ahead and move on to the next question? Do you have any feeling?
It's not a debate, we just go to the questions.
Right. So why don't we just go through and you can address some of the points made from the con side and vice versa. Neal, you.
Okay, so I would like to make a few remarks about that. So there was this example of the boat that is living around, and I think it's a nice example. It shows that we will, as I said, never have perfect reversible computation. So these informational degrees of freedom will always couple, of course, with the rest. We can never perfectly isolate it. And that's, of course, exactly also, as I said, the problem we have when we build quantum computers. So what all these experimental groups that are trying to build devices that are good for quantum computing are trying to do is to mainly isolate their system from the rest. That's one of the important tasks, and they will never achieve that perfectly. But for that, we have, of course, methods also from theory, like error correction. And error correction, of course, means that you still have to invest energy from outside into the system and pump away entropy in some way. So I absolutely agree with you that we have to correct for these things. The question is just, is there a fundamental limit to that? And let's again take this example of a boat. So I could now say there's also improvements to that. Let's take a spaceship. This is much better isolated, and the type of correction, I still need to do correction, is when I let the spaceship travel to Mars. But the corrections are much smaller compared to the actual energy that is in the whole system. And so even in that case, I would say there's probably no way to find an absolute limit, a fundamental limit. While I would certainly agree that any spaceship will always need some small corrections. But my point is there's no fundamental limit, and it's just a technological issue to limit that to small values.
Should I respond to that?
Yeah, if you want to. Sure.
Okay, great. Sure. So I think we're actually very much or close in agreement. So there's an analogy to the spaceship versus a ship on the ocean. relates to the size of the thermal fluctuations. So you, of course, have to design your system to withstand whatever thermal fluctuations there are. So that corresponds to temperature. I mean, if you, let's say, the ocean corresponds to high temperature, large fluctuation, a spaceship up there, small fluctuations, corresponds to a low temperature. And of course, you have to dissipate less as the temperature decreases. So I'm totally in agreement with you. But still, the point is, you have to deal with the thermal environment, the KT environment that you're in. I also agree with you that it's hard to come up with a fundamental limit for manipulating a bit, how to change a bit. I think the only fundamental arguments that I've seen relate to reading information across a noisy channel. In my opinion, that goes back to the arguments of Szilard, but it really sets a lower bound. Practically, you're going to have to dissipate much, much more because there's more to computation than just the read operation. But again, the only fundamental argument that I'm aware of relates to the read operation, but that doesn't mean that that's the most important energy cost, which I'm sure it is not.
So do you believe that the reversible computers violate thermodynamic principles?
See, the thing is, as I was trying to point out during my talk, I think that there are different levels. So there's the physical level of the computer, and there's the logical level. And those wants to be very careful going between those two. So I think logical reversibility is actually irrelevant to the computational process. And to just say that one more time, computation is a step of bit operations. And there's a logical, overall logic related to the computational process. Arguments related to Landauer and logical reversibility don't deal with the bit operations themselves. They just deal with the overall logical structure of the computation. And that is irrelevant. What is relevant are the actual bit operations.
Can I ask a question?
Sure.
In regard to the analogy spaceship versus a ship in the ocean, isn't it the fluctuation, how much effect it will produce depends on the mass, for example. So if you have a massive system, then the thermal fluctuation would produce little effect. And if it is less massive, then it will make an effect. But if you have a more massive system, then it will take more energy to move it to do the computation. Is that to be accounted for?
Oh, I can address that. Basically, it's not the mass is important, it's the thermal relaxation time. Thermal relaxation time. So in electronics, very easy to see. There's a capacitor and there is a resistor. Okay. So if you take a resistor, there's a thermal bath, put a capacitor parallel, then it's always, independently of the size of the resistor, you will have the mean square noise on the capacitor will be KT over C. Doesn't matter how large is the resistor. The resistor is a friction, and the thermal bath, that will just control how fast are these fluctuations. Okay? The capacitor is a mass. The resistor is the friction.
Right. But so, when you do the computation,
yes?
each step, something is moving, right?
Yes.
So you know you're doing a computation per step. Does that take energy, or is that energy counted in what you're talking about?
This energy is when you change the state. The stable state of the computer must be, the state of the computer must be stable, otherwise the number would run randomly on your display. Okay? So when you compute, then you have to kick the state between stable states. Okay? So and to climb up on a potential barrier, you have to invest this energy. Yeah. And when you get done in the other well, then you have to dissipate energy, otherwise the system would come back. So that happens. There's a friction. That's why you need the friction. That's why you are coupled to the thermal reservoir. You can't avoid that. If you try to save this energy, you dissipate much more due to the need of control, time control of getting back the energy.
I just have a question to pose about that. Is stability of intermediate states absolutely required for computation? So if I have a box and I can encode some number in it by dropping billiard balls in one side in some pattern, and they go through the black box and they fall out the bottom in another pattern that's the prime factorization of what was represented when I dropped it in, and it does that every time and it does it correctly. Is it required that in that black box the the balls are stopping and sitting in some stable state and then going to another one and sitting in another stable state? I mean, why? For computation should just be a mapping, a defined mapping from some input set to some output set, and that instantiated physically, if you're talking about a physical computer. Is the stability of intermediate states required?
There are two issues here. One is that of course only those degrees of freedom are important that we discussed, which takes part in the logic operation. Other degrees of freedom are unimportant. Second one, the example is not very good because this is an automaton. So like basically, if you let the ball go into there's a pattern here, geometrical constraint. You put your ball here, and it goes to this part. It's not a computation. It's an automaton. It's like a analog computer. It's not an arbitrary unit. Basically, when you put this geometrical constraint in the system, you already put the solution there, and the ball will just follow that. It's automaton. Yes.
I'm going to push back on that a little bit, because what if it works for every pattern of inputs that you want? I mean, an ALU. It's not a computer in the same sense that an ALU is not a computer. It doesn't run a program. It's not a Turing machine, but it predictably produces outputs for any input, according to some mapping rule.
This is analog computer. So this is actually in a quantum computing debate. I will bring this up. See, if you have a general purpose computer like this computer here, and you want to simulate sinusoidal oscillator, okay, you will do it. Say you can do with maybe, I don't know, 1 megahertz speed, and you dissipate like 100 watt for making a sinusoidal signal with this, and this high accuracy, say 32 bits accuracy or whatever. Okay. Now I can do the very same. I just take one transistor and a few capacitor and an inductor and the 3 resistors, and do the same at say 100 gigahertz with say 1% accuracy, with say 1 picowatt or 1 nanowatt dissipation. That's an automaton or analog computer. It's called analog computer. It can do only that one. It's not a special purpose computer. It's a system basically which is doing its own processing. No new information. You can. As automaton is the proper name or analog computer. Analog computer is like quantum computer. You build a new computer for each task.
I understand the distinction, but I don't really think what we're talking about here is whether reversible general purpose computers are feasible, and we're accepting that reversible special purpose computers would be feasible. We're arguing about the possibility of doing computational operations.
I just addressed your example of these pooling balls, yes. which actually is even dissipates energy. This is why I brought up this other example with the RC resonator circuit, which would do your sinusoidal function for infinite time without any energy. Like if you think that there is no loss in the LC circuit.
You could even have talked about the box with balls that does universal computation. No one has built such a box, but the question is, could there be kind of such a black box that takes as input some arrangement of balls, arranged such that they encode a program, and what you get later after certain time computation?
I think stability is always crucial, because if you do not have stability, you always have this effect that you can have exponential many answers.
I didn't mean that its behavior can't be predictable. I meant a minute ago we were talking about intermediate states being stable. And I'm just asking the question, does computation require that intermediate states be stable, or does it just require that you put an input in and at a later time the correct output comes out?
I think it's exactly this mechanism, because with any step where there is some instability, you get exponential growth of this instability. So this is like an chaotic system.
So by a step, you mean at a time? Not a time interval, during a time interval.
It's a unit of time, yes. So I mean, you can think in continuous time computation or discrete. It doesn't matter.
And the degrees of freedom with logical role are important, because it may be that in certain direction the ball can freely move, and who cares? There is it. it will not come in the output. So though that degree of freedom is not related to the logical state.
I think I would perfectly agree with what you say, also what you say about this exponential growth of the phase space region that we are covering. But this is exactly what, for example, quantum error correction is trying to avoid. So there, after each time step, you do a special purpose correction step that actually has exactly this effect of keeping this exponential growth of inaccuracies under control. So I would agree with what you say, but I would say we have a countermeasure against it, and the countermeasure is error correction.
No. Error correction is not really error correction, because if you, it's error prevention. So you want to design somehow the Hamiltonian of the total system, make it more complicated to avoid this kind of phenomenon. But usually the effect is opposite. If you make system more complicated, this is more chaotic and is more unstable with respect to permutation, to perturbation. And I think that the main belief about quantum, I'm sorry that I return to quantum computing because I will be not present tomorrow, but it is, somehow it's related to reversibility very strongly, and there is no difference essentially. The main problem is that there is no threshold. So-called threshold theorem produce threshold because they have assumptions which are never satisfied in a physical system. And even the people who did it, they agree. But they hope they can improve it. So this is a complete artifact of the initial assumption. The theorems are probably correct, but there are only few people who check it. But assumptions are physically wrong. And I think there is nothing to be... so in this kind of approach, when you think about quantum chaos, the threshold is energy spacing, average energy spacing between energy level of the system. So we know that it decreases exponentially with the size of the system. So if you have a fixed error, whatever small is, for large enough system, you do not have any threshold for the protection against instability of complicated systems. And I think somehow the people on this field do not want to study this. There are papers in the 80s and 90s about this topic, and they are simply completely forgotten.
So when you mention intermediate states or steps, and you say that they're unstable or metastable, are those deterministic?
Well, I was just responding to the, as the discussion went forward, we were talking about, stopping at a certain point to let, to waiting for the gates to be finished and everything. And I'm asking the question...
In the transient time period or something?
Yeah, I'm asking the question if the notion of computation requires that you stop. It certainly does if you have a pipeline or if you have gates or something like that. But if there's another way, I'm asking, is that a requirement? And I personally don't think it is. I don't think it's an a priori requirement for a computation.
I agree with that. Especially nowadays, there's more and more interest in chaotic computation, and it is still stored only at the surface. But I think there is a lot of potential in that. Definitely, it's possible.
So I have a question for the Con team related with this. I think that right now there are very general and very rigorous proofs of lower dissipation bounds for certain operations and assumptions about information loss. I think there are a variety of them, and they may differ in the definitions or whatever, but they're there. The assumptions are clear, and there's a result, and again, they're lower bounds. How do you think equally rigorous bounds can be obtained on the dissipation that would occur in reversible computation? Can you get rigorous results? So if the thermal fluctuations are there and they're going to derail things, how rigorous can we be about that? And it's not a rhetorical question, it's a serious question, because the kind of work that I do, the thing that gets me interested in reversible computing ideas, even if you don't go all the way down to zero, is that you do better than you would do in an implementation that involves irreversible logic. So I get excited if you can show me a rigorous bound that and it's higher than the Landauer bound. Then I change to that side of the table. I'm just wondering if you think that's possible, or if the nature of or if it depends on too many unknown things to be able to say, or
do you take fluctuations and noise into account to your models?
Yeah, they handle a noisy system, but they don't tell you how much noise is going to be in a given system. They can handle a situation where it's there, and you want to know how that affects what gets dissipated when you do an operation. But that's a different question. So I'm wondering how.
First of all, I think that reversible computing is possible. So you say that I should imagine a reversible computer. How much would it be the energy dissipation?
No. If you designed a system that was supposed to be a reversible computer,
it should be logically reversible.
Yeah, logically irreversible, and you're going to run. How rigorous a bound do you think can be produced on how much dissipation will be there?
Probably a logically reversible computer would be more complicated structure than just a straight computer, or is not?
No.
It could be maybe a simpler structure.
Actually, it has to kind of record previous states. So maybe it has even more hardware. It requires more hardware. More hardware implies more energy consumption.
Okay, so there is a limit. Then there is a limit. The limit would be a normal computer. There's a lower limit. A reversible computer would dissipate more energy.
Well, but can you prove that? I mean, a normal computer, meaning a logically irreversible one.
But he says that the reversible computer would record all the operations. Yeah, that's extra job.
I think hardware complexity is higher than a normal computer.
Well, there are counterexamples to that, like whether one believes in it or not. One proposal is Bennett-clocked quantum cellular automata, in which case the hardware is the same, and all that's different is the clocking strategy.
Don't believe in it.
Well, no, we could argue about that. That's not the question. The question is how rigorous a bounds do you think can be produced on the fluctuations? Again, it's a serious question. It's not a rhetorical question. I'm wondering how good a bounds you think can be obtained for the thermal fluctuation.
My point is simply, as I mentioned in my talk, it is each operation kt times logarithm 1 over epsilon. Epsilon is error probability of operation.
So I agree completely. Yes.
So basically, you have to count down how many operations it needs and multiply it by kt times ln 1 over epsilon.
Somehow, your answers remind me of this picture that you had in the talk of this little airplane. Because, of course, I mean, the picture suggested this is something completely unrealistic, this steam engine airplane, but today we have airplanes.
Yes.
So it shows that, of course, you go into this question with a certain conceptual view of how these things should look like. And you're now talking about the number of operations and so on.
Yes.
But there's no reason to believe, as you just suggested before, that there have to be stable states in between. I mean, it could be some continuous process, and then your argument would not work, because you simply cannot count the number of operations.
Yeah,
so what one would expect by rigorous proof is something that just only assumes we want to do the computation and doesn't include any other assumptions like that the computation has to consist of steps and stable states in between and so on.
No,
and
basically,
if you have that, then it would also change the side of the table. No, but as long as you are making these assumptions, then I don't see why this should be rigorous.
But I say the lower limit is number of binary operation multiplied by kt times ln 1 over epsilon. Now, if you have some continuous operation, then I don't know. That depends on the operation. But the number of binary operations, each of them will dissipate this energy. And if there is more operations which are not binary, then they have some extra. So that depends on the system. I don't know.
Yes. And if you want to have a proof, you need some assumption, if you propose some new way of computing with some new kind of device which doesn't use steps, gates, and things like that, then one can analyze it. I mean, at first one have to
See.
when it's modeled to see it. I mean.
Also, okay, so you're only saying with the current computing model, it's not possible.
No,
it's not physically possible.
No. I mean,
I suppose that if there is no dissipation at all, then that means that this is a Hamiltonian system. So it's like a ball which moves in some potential profile. So we could imagine that we would construct such a potential profile that the final state or the whole trajectory will give some answer to some computational problem. But somehow, and then there will be no dissipation. We'll just watch the trajectory.
This is what I call an automaton.
Watch the trajectory and this
It
will
does
give us
one thing that it was designed for,
this one
but it
will
doesn't
give
do
us
anything
the
else. And it's
Well,
not even.
I think that the answer that it will give is what is the trajectory in this potential. That's all.
It gives the answer that you designed it to give you in the first place. So you know the answer before you actually design the computer.
I think that
So
It is zero
there's no
energy,
point
doesn't
in
even give an answer.
Precisely.
But it is zero energy, doesn't even give an answer. Just it fluctuates
yeah.
between input and output.
You
state.
invest some time.
You need to stop it somehow. Yeah, I mean.
It's the only way when you don't have any dissipation.
but then you have chaos, so you cannot predict the trajectory.
Well, if you have just one ball rolling,
But you have to establish initial state first. There is a finite accuracy, yes? So then,
with exponential.
then you have exponential growth, possible
I think,
outcomes.
I think that's a little too easy, though, because you could say exactly the same thing about a computer. If it's programmed, a computer's sitting there, it's programmed, there's input data in a register, it's just some arrangement of charges. You push the button, it finishes the computation, there's just some arrangement of charges. And of course it calculates the result that it's supposed to calculate. That means it's working. But you can put different initial sets of charges on there, and it will give you a different final set of charges exactly as it's supposed to, which means it's working. It doesn't mean it's like an apple falling through free space. It means it's working.
It doesn't mean that I can calculate it.
No, but it's,
Right. No, but that's
it's completely different situation, because in real computation you have attractors and you have basins of attraction, so you do not have a single point. So it's enough that the final state particle is in this basin of attraction and finally asymptotically comes to this fixed point or limit cycle. So this saves standard computation model.
Because of that, it consumes energy.
And because of this, it consumes energy.
Well,
and
but
this is exactly this energy.
No, I understand that difference, but it's a different difference than the one we were just talking about, I think, because if you had some, I'm not making a general argument for Hamiltonian or billiard ball computers, but if you had some contraption that did what I described before, and you have a camera and you photograph the balls flying by as they come out the bottom, and they exhibit the right pattern, they don't have to have gone into an attractor state. The dynamics just have to have been correct in between the input and the output. And so that's...
Do we discuss the Turing machine now? Because that, I mean, I thought that the
this I'm not talking about a general purpose
You
computer.
want to get rid of stable states, but I think the important is whether it's deterministic or not.
Yeah, right.
Determinism is also determined by fluctuation.
Yeah,
Influenced by fluctuation.
I
So
agree.
we can't
No, I-
reason this away.
I agree completely, and again, back to the question I posed before, and I'm honestly interested in this question, is that if you have a computer that evolves, it's a reversible, designed to perform reversible operations, and you can embed irreversible operations in reversible ones, and it exhibits some unpredictability because it's coupled to an environment, but not enough unpredictability that it doesn't serve its computational purpose. That's interesting. And so the question is, how well can we quantify what the consequences are of those fluctuations for the computation, so we can compare it to what the costs are that come from the logical irreversibility of the computation, or however you want to put it, if you believe in that.
Well, if such a research program is started up, I'm all for it. I don't expect anything.
We can agree on that.
I don't expect anything to come from it, but
why not?
Well, why not? It is intuition, but.
So the minimum, I think that I would bet the minimum information would, minimum dissipation would be absolute minimum, the Brewery limit, Negentrop limit. So KT times ln2 multiplied by the number of bits of new information the computer produced.
You had a question?
Just a comment about the billiard ball computer. I was just thinking it's going to possibly need stable states. Just think of an operation like 2 times 3. You're going to put 5 balls in and 6 has to come out. So you're going to need a state in there somewhere. And also you've got to program in the operator times somehow as well. And so you're going to need states to do all these things, surely.
You have some encodings of the information, so anyway, the same number of balls have to come out as come in, because it's conservative. But you can encode it in such a way. I think even if there are stable states, you can encode things. So if a billiard ball is stable and another comes, it kicks, this becomes stable, and this one goes there. So depending on which angle they make, it goes in a certain direction. So basically that is possible. I don't know whether you can completely program it as a Turing machine. Maybe not.
See, in a billiard ball computer, you need bars for intermediate computations also. Say there's some information carrying bars, say 2 times 3 or so, and then these bars have to bounce in order to give it the answer in the end. In order for these things to work, you need certain logic gates along the way. And in order for these logic gates to work, you need auxiliary bars, which you have to start in the beginning together with your input, say the 2 and the 3. And so in order to do the billiard ball computation, you have to know beforehand what the computation looks at each state in order to start these auxiliary bars exactly at the right location, at the right time, aiming at the right point. And so it is not general purpose at all. I mean, it is.
And each of these collisions will be random,
yes,
partially because of the thermal noise there.
It's extremely unstable.
Yes.
It can produce some probability distribution, but not the real answers to many problems.
Which will grow.
This is why I excluded things like that, like billiard ball computers, from models of computation explicitly.
Is everybody, okay, you had a question?
Put like an analog computer as an example of a continuous system that perhaps couldn't sort of provide the properties that you're looking for, circumvent this issue of having to have stable and uniform.
But I also think actually a quantum computer, the way it's designed, it has in some way no stable states, because I mean that was always a concern because people studied error correction or fault tolerance. The concern was that a bit can be in an arbitrary superposition, for example, between 0 and the 1, and if you have a computation where it has to be either a 0 or a 1, then people thought we cannot do correction because we cannot analyze whether it's 0 or 1. There could be all these intermediate states. And so now, as we know how error correction could work, and I, by the way, agree that there are some assumptions to error correction, and we can discuss whether they are reasonable, but under these assumptions, we know that we can correct for such errors, despite the fact that quantum computation is in some sense analogous, because they're always, quantum mechanics never allows us to project onto a certain state unless we would introduce a measurement, which would be.
How do we know this?
But I mean, it could be, but let's say in the formalism used to design quantum computers, you just use unitary evolution. And despite the fact that we have a completely unitary evolution, you can correct errors. And so that's maybe the same as what analogous computers would do. So yes, I think analogous computers with such a kind of error correction, as well as quantum computers where error correction has been analyzed and studied extensively, show that at least the principles are there. And now, of course, one can question the assumptions. That's reasonable. But what I would like to hear then is to have an explicit statement why certain assumptions are fundamentally wrong. I would also not say they are proved. I mean, we have to build quantum computers in the labs, and people are doing that. And before they work, we are not sure whether the assumptions are really justified in physics. But on the other hand, we also know principal reason to be against them. So I think we should just see what happens.
There is, I have just put on archive, this is a chapter from the book on error correction. So the organizers of the conference allow me to write the final chapter about the criticism of quantum error correction. And there are presented arguments why the assumptions are wrong. So they are generically wrong. They are never satisfied for simple reason, because to have error correction and threshold theorem, you need the exponential decay of correlation functions for the reservoir. And this is never the case. You have always power-like tails in any physical systems. At thermal equilibrium, you have always power-like tails for autocorrelation function. And this kills completely the basic assumption of error correction theory.
But it's
this is
still not
ignored,
proof
you know.
that it doesn't work. It's just, even if this was true, it would just show that the current error correction schemes that we have don't work. But it wouldn't prove that there's a fundamental
You cannot prove that something cannot exist. This is, you know, no-go theorems are always under some restricted assumption. So this is on your side the burden to prove that with realistic assumptions this can work. I can only pinpoint the wrong assumptions.
You gotta follow up.
Yeah, there's you can do universal quantum computing but without error correction, because you can implement just Clifford gates with magic states, they're called, and then you don't need to do, basically you're using a resource.
To prepare magic states,
You know, they call it
this is impossible to prepare magic states. This is why. You know, the problems are always in different model of computation, the problems are shifted to another coordinate.
It's not, I mean, we use the term magic. It's a nice
I know this theory. I know exactly. I know there are states of large system which have some quantumness there. So it means that, for example, with certain representation, this quasi-probability distribution in terms of coherence state is negative somewhere.
Wait, quantum computing is for tomorrow.
Yes.
But he is not here tomorrow. So.
Yes. I mean, all these schemes, they have isomorphic flows, because they are isomorphic from the computational point of view. They also have the same problems, but in different places. So the preparation of, for example, magic states, or preparation of what is called fresh or cold qubits, all these things are never proved. And this is on your side of believers to prove that this is possible in a reasonable physical system. I can only say that in my opinion is impossible, and I can even give some argument, but I cannot give a general no-go proof that I think nobody can give.
But then I'm actually perfectly happy with the discussion, because I thought you have a general criticism that would a priori exclude all that. And I also agree that it's up to those who claim that quantum computers can exist to prove that they can exist, and that's why we have hundreds of experimental groups trying to do that. I think that's exactly what they're trying to do. And in 20 years we will see the answer.
Yes, but that's,
I cannot claim we have it already.
It took already 30 years, and the progress is infinitesimally small. How big quantum computer exists now? 3 qubits, 5 qubits, it's maximum. Really, completely controllable. Without cheating like in NMR case that there is some, you know, classical computation before to design the pulses or things like that.
So you
5
have a
qubits
question.
after 30 years.
So I'm interested in the ship on the ocean. So developing a high performance ship is like error correction. So error correction needs a lot of money and cost. So rather than that, engineering the environment. By engineering the environment, this floating ship can do some computation. So a same floating boat can do something. In my opinion. By engineering the environment.
Freaks the ocean.
For example, this ship may be able to find some food or something.
And I think
Optimization.
I think this is what some of the experiments are. The one that I'm familiar with, in particular, this is one of the questions that you asked before, engineering the environment. So one of the papers deals with averaging the environment, which is sort of an engineering of the environment. Of course, this is nice because all of a sudden the ocean is not the ocean anymore; it's completely flat, right?
Not
and
that,
then you
not
can.
that. Ocean needs to be
But if you engineer,
Yeah.
but this is what one of the papers is about. So I'm just saying, one has to be careful in looking at the claims of some of these papers.
One word about engineering environment. I mean, this is a contradiction. Environment is something which cannot be engineered. You cannot engineer something, it's a part of the machine.
Right. That's right. Yeah, I agree with that. Yes.
So there is hundreds of completely wrong papers about engineering, dissipation, and things like that. And it's basically wrong.
Of course, concerning your comment about 30 years without a progress in experiments, I have to contest that. So this you cannot put in the trash bin like there's so much progress that has been done in the last year. I don't know if it's 30 years or something. If experimental progress in fighting the coherence was insignificant, we wouldn't have Nobel Prize winners on exactly this theme. So it's extremely difficult to harness, of course, nature and to prove the coherence does not. We can fight, we can control the coherence at the quantum level, of course. I will totally agree with this. But it is not impossible. There is exactly none of you has said there is any fundamental limit to that. Experimentalists are working in this direction. There has been lots of progress. There are 16 photon experiments happening right now, and even more are going to happen in the future. Okay? So, and these states, even complicated states that are required, are not going to be perfectly generated, never, but they are going to be generated with some fidelity. This is usually what characterizes these states. Together, theorists and experimentalists, with these fidelities, with these probabilities that we can generate experimentally, and with the bounds that that are becoming better and better in error correction codes, I think it is very likely, exactly like Renato is saying, that in 20 years we will have something a lot more closer, let's say, to reality that we will be able to show. It's up to us. I agree with you, but I mean, it's unfair to say that there has been no progress in this direction.
I mean, there's enormous progress in technology, and in control of small systems, but it's infinitesimally small from the point of view of quantum computation, because you need much more than it's.
I mean, we have to start with somewhere, right? we need. If we can prove that we can control at this level bigger and bigger systems, fine. We're not at 1,000 qubits. I agree with you. We're not at 1 million qubits. This is going to happen together with error correction, of course, and everything. But even bigger, we can control better and better, bigger and bigger systems, and this is how progress is going. Right? There's nothing that tells us that this is not possible.
There is something, because somehow we forget that.
Listen, if this is a debate about quantum computing.
Okay, I'm sorry, because it's my fault. Yes. Okay, let's stop.
So are this on the small scale quantum computers that have been this is going right to the original. Are they reversible? Like the quantum computer that factored last year 21 into 3 by 7. Is that reversible?
No, no.
Yes, I would say any, I mean,
It cannot be
easy to see. As soon as the system on which you do the computation or the information degrees of freedom interact with the environment, you have decoherence, and therefore you lose the quantum aspect of it. It will essentially be a classical computer. So if the claim is correct, then let's say if you build a machine and you can reasonably claim that it's a quantum computer, then it's automatically a reversible computer.
So does that settle the I mean,
so it just means, I think they said that at the beginning, that if we can build quantum computers, then you can also build reversible computers. Now, obviously, the debate is also whether we can build quantum computers, but there are at least.
What about the ones that have already been built? I think
they are reversible, but they are not full-fledged computers. I mean, they're very small machines, and I think that's why the experimental proof of their existence, of the existence of scalable quantum computers, is certainly not done. I mean, this is something to be done. We just have experiments, and I also disagree with you. I mean, I think there was a lot of progress in experiments of small systems here, and the progress was actually enormous. I mean, if you look at how many different systems we have, I mean, starting from Eintracht, superconducting qubits, we have many platforms, optical systems, and so on. And all these systems work, but they all really work only on a small scale. But on each of these fields, there was enormous progress in the last 20 years. I think 20 years ago, you would, for most of these systems, have had many people who would not believe that we can actually control these degrees of freedom. And now it's clear we can control them. Now the remaining question, can we put these systems together? Now we can very well control the individual components, but the next step is to put them together onto one thing. And this is already an enormous problem.
Is the problem.
It's two steps. One step is to build the individual components, the other one is to build...
All of them are scalable. There's very few systems that have been proven to be non-scalable.
I very strongly disagree that the computer is resolvable. I mean, Giulio Giovanology proved that Giulio Giovanology is the editor of Physical Review A for Quantum Informatics. His famous paper proves that the quantum computer, the energy dissipation in quantum computer satisfies Heisenberg relation type relation, where there is h times f frequency of the operation, and there is a 1/error there, epsilon. So depending on how much is your error of your quantum gate operation, there is a well measurable dissipation, which is actually much more than the classical. That was our joint paper. We showed that general purpose quantum computer would dissipate about 1,000 times more energy than the same than a classical computer with the same performance. That's his famous result. The expert of ultimate expert, he's famous for this.
So you're saying the quantum computer dissipates more energy than the classical one?
Yeah. Yeah, it's the general purpose computer. I'm not talking about Shor algorithm because that's a special purpose, so that would be much less dissipation than a classical computer doing the same. But the general purpose quantum computer would dissipate about 1,000 times more energy than the classical. Due to all the error correction, I can send you the paper.
But there are no algorithms for a general purpose quantum computer, so there is no sense in making general
there
purpose
is.
quantum
It would be the same algorithm because those quantum gates you can use in a normal computer too.
Yeah, but you can just run the same kind of computations.
Yes,
so
and then it would dissipate 1,000 times more energy.
Yeah.
So the point is that it dissipates energy. A single quantum gate, the quantum gate energy dissipation is scaling with 1/epsilon, while the classical computer dissipation scales with logarithm 1/epsilon. So that's the big difference. So it goes to the infinity. When you decrease the error probability of quantum gate, it goes to infinity. So like if you we evaluated how much would be the energy dissipation just running a single quantum gate at the same error probability as a normal gate in the computer at 10 to minus 25, it would be the same energy power as New York's household and all households in New York. Of course, they don't want that. That's the reason why they don't want to have such large energy dissipate, such large accuracy. They are filling with 10 to minus 4 or something, or 10 to minus 3 accuracy because of to avoid this very large energy dissipation.
Laszlo, I have a better argument than that. My argument is it's not possible to have a general purpose quantum computer, but I'll save that up for tomorrow's debate.
Yeah, why don't we wrap this debate up today, because it seems like it's sort of heading over into the quantum regime and quantum territory. Save these debates for tomorrow. So do we want to do just a brief kind of point-by-point summary, or just how about if you just have any final comment that you want to make just to kind of wrap up tonight? It doesn't have to be anything rigid, just anything off the cuff that you want to add.
Yeah, I guess I'd like to just make a few comments to finish up. But back to the notions of Landauer's principle and irreversibility and so forth. I think it's kind of an interesting irony that that Landauer's principle, which that many people even knew about for decades, only a small number of people, is suddenly controversial right now when dissipation in computation is suddenly this topic of huge practical importance. It's where multicore came from in the first place, although that was dissipation from parasitic sources. You don't have to go too much further to see that following Moore's law, if it had kept its previous trajectory, you run into the fundamental limits, as predicted by Landauer's principle, around 2020, give or take so many years. So it's interesting that this has become controversial at this point, and we're still arguing about it. So the question is, why are we still arguing about it? It is a hard problem, and it's a subtle problem, but people do hard things and navigate subtleties. So I think the reason is that we people at different points of view haven't communicated enough and precisely enough and tried to translate each other's arguments into their own language and understanding. And I think our goal should be to do that. So when we are, let me just finish this sentence. So when 2020 rolls around, the only workshops that we'll be able to get our talks on Landauer's principle in will be at cold PI. We should be victims of our own success.
See, the current computers dissipate millions of KT for per operation, so this is rather the KT times ln2 energy of Brillouin, not Landauer, is irrelevant.
I would say this debate is probably undecided as long as we haven't experimental tests of that. So there's on the one side people who claim that there are some fundamental limits, but as far as I can see, they agree that we cannot have general no-go theorems. That's what you said. So we don't know whether there's a no-go. On the other hand, I cannot prove that the quantum computer exists until it's built. So I guess we need people like the experimentalists, like Alicki and others, who examine this question experimentally. And I think this all shows that we should actually invest in this idea of quantum computation, which is, as I said, implying reversible computation to make this link. And until either this side here finds a convincing general no-go theorem, but they already admit that this cannot exist, or until the quantum computer has been built. So I think it just shows the need for experimental work.
Final for you.
Concerning Moore's law, I think it is very important. It has been asked to Moore many times when he worked and is still working in Intel. How long will this law be extended? And his standard answer was 10 years, and that was in the 1970s, 1980s, 1990s, and it was always 10 years. And so it's amazing that it still goes on. And I agree with you that heat dissipation will be a huge issue. It is already a huge issue. So I think it is important to think about it, but I also think it is important to take into account fundamental issues like fluctuations, noise, and so on. And well, if that is taken into account, I can agree with a research program like that.
Okay, maybe returning to Landauer principle, I think that the Landauer formula gives us connection between thermodynamics and information by this logarithm 2, and I think this is strongly misleading. I agree with Wolfgang that information in entropy in information theory is something completely different than entropy in thermodynamics. There are some relation, but they're on the completely different level of stability and efficiency and things like that. And imagine at the end the example. Imagine that this table can stay in this corner or in the other corner. Before you enter this room, you don't know in which corner it stays. Then you enter the room, you've got one bit of information. Can you extract a word from this? No. Thank you.
Okay, I think I agree. Everyone here believes that the questions of energy requirement and computation and ultimate limits, those are important questions. And in order to work on those in a meaningful way, I think it is misleading to invoke arguments of logical reversibility or irreversibility. What one really has to do, and it sounds like a trivial statement, in order to talk about the energy requirement of computation, one has to look at the physical computational process and look at the energy requirements that are related to a particular physical process and not the overall logical structure.
Okay, then I would just mention three things that I think we can summarize Wolfgang's talk, that the computers are not ergodic systems. So this is thermodynamical entropy just is irrelevant for them. So concerning Moore's law, it came up Moore's law. I had some work on it. And the reason why they can still follow what they do is because they stopped increasing the clock frequency. Back in 2003, it was 3 gigahertz already, and then the chips started to smoke, so Intel had to stop, go back from 6 to 4 nanometers for some time, and we are still at 3 gigahertz, even though with the concentric size it could be around 12 gigahertz now if we would really use the bandwidth that is possible. Now, concerning the quantum computers, it's a famous result of analogy that the minimum energy dissipation of a single operation of a quantum gate is h times the clock frequency divided by epsilon, the error probability. So it's fairly non-reversible. It has an energy loss. Thank you.
Okay, thank you very much. I'll conclude today's debate and continue tomorrow with the quantum side of the equation.
I thought we were talking about Landauer tomorrow.